Hello everyone. I am Ch.Nagendra Mahesh. This is our second project, hardware acceleration of Fourier FFT using systolic array architecture. In this project, before the demonstration, let's get to the concepts behind the DFT and FFT and why we use systolic arrays. So, these are the contents in these slides. We will discuss about the historic array fundamentals and FFT's time complexity and DFT's time complexity and processing elements architecture and how butterfly computations are happening and the data flow in the FFT architecture in the systolic arrays and the performance analysis of all the architectures. Yeah, so yeah, so this is the DFT generally that we do for calculations. For this, the generally the complexity will be around n square complexity, but this complexity is very high for large values of n. So for that to improve it, we use FFT. When we use FFT, our complexity will be reduced to n log n. So this is the complexity comparison. Yeah, as you see for n equal to 1024, the complexity for a DFT is 1 million. But if we use FFT models, it will reduce it to 10,000. So the change is very high. And in the FFT models, we can use different FFTs like the generally what we use is theoretically Radix 2, but Radix 2's complexity is around 10,000. So we can further reduce it using Radix 4. That's the idea for this project. And when you use Radix 4, the complexity will be further reduced. Compared to Radix 2, it's 50%. Compared to DFT, our Radix 2 itself is more than 100 times. So it is more than 200 times. Yeah, so let's see how FFT architecture is like. So in a FFT architecture, let's say we have an endpoint DFT. We will divide it in a particular in the stages. Let's say we have 1024, so we will divide it into 10 stages. In each we will compute the twiddle factors for each, and we will do the butterfly multiplications so that we use the data from one stage to another stage. The Radix 2 will have 10 stages, but for Radix 4, it will be the number of stages will be less, but the computations will be high. So that is the difference. Yeah, a systolic array is a grid of processing elements. You can see here how the systolic array architecture will be. It will be a series of blocks. So it will be helpful in parallel computations. These are generally arranged in 1D or 2D architectures. So all the clocks for these processing elements will be synchronous. Yeah, so in each PE, we will calculate the butterfly calculations like the twiddle factor calculations and everything. And these results are passed to other PEs. And this will be very helpful. Since these are all in parallel processing, uh, after the initial few clock cycles, the data will be ready. Like in each processing elements, the data will be stored in its local register. So this will be very useful. We can see the comparison here, how the systolic array computations will be and in the traditional GPUs computations. In the systolic arrays, the data movement will be in the neighbor to neighbor, like in the processing elements here, the data will be moved in its neighbors, whereas in the traditional CPUs, each data will be accessed from the global memory. So this causes the delay and latency for us. But when we use systolic array, these data will be uh, near to us, so it will be accessed much more fast. But the issue will be the increase of hardware architecture. Uh, the parallelism will be the systolic array, its parallelism is like a pipelining architecture. So it will be very similar to us. And we can see how data is between in the FFT for the systolic arrays. In the cycle one, first we will calculate the P, and this data will be flown to the cycle 2, like in the to the other stage. When the these other stage data is like an input to this, the other data will come into the stage 0. This new data will be computed parallelly when the computations in the stage 1 are being happen. So in such a way, like let's say for n values, the number of stages will vary. For different n values, different stages will be there. Different number of stages will be there. In such a case, these parallel as n increases, this cycle will be very helpful. You can see the processing elements architecture here. You see here, we will calculate the twiddle factors and everything, and the adding and subtracting. Like once we calculate the twiddle factors and multiply it to the stage inputs, these values are added and subtracted. Like since we are using complex numbers as inputs, the additions and multiple complex additions will be done here, and the data that is done in the here will be given to local registers, and these data will be stored so that it will be helpful in the future. And this is how radix 2 operations will be there. In a radix 2, when you are multiplying, one operation will be the plus, and the other will be minus, like but in the radix 4 architecture, this will be a different case. So the arithmetic operations will be different with the twiddle factor coefficients. So this is how the PE communication will be like. These stages in each block, there will be the components of the multiplier, adder, and buffers. These will be calculating the elements, and the data will be stored here, and this data will be passed to the another PE, and that is how our systolic array calculations are being done. So let's see the performance analysis. So let's say for radix 2 we have 10 stages, but for radix 4 the stages are reduced, so the complexity and the timing will be reduced. And the throughput, if we discuss, like it's based on the clock input. Let's say we have a 1 gigahertz clock, our outputs will be 1 billion outputs per second. So since although we are in systolic architecture, there won't be any stalls in the pipeline that we are using here. This is the total execution time based on the uh, number of points we have. This will be the number of cycles we require. Since we are using systolic array architecture, there will be no DRAM access. Like all everything computations will be done in the local calculations, so there won't be anything like if you compare it with the traditional GPUs, you will have the calculations uh, taken from the global memory, so you will have the DRAM access. This will cause the delay, but in systolic architecture you won't have anything, so this is quite an advantage for us. So if you compare the memory architecture, like in systolic arrays, as we discussed, there is no global memory usage. Buffers will be used for this. Buffers, local registers will be used, and twiddle factor storage, we will store them as a lookup table, so it will be very easy. Since we are not using any global memory, the memory bandwidth requirement will be also very less compared to the traditional FFTs. As you see here, the in the traditional FFTs, the global memory access should be done very frequently. This increases the latency. The buffers and local registers will be very less, since like the data we are mainly getting from the global memories, these uh, usage will be very limited. Twiddle factors will be computed every time it needs, because they don't store the data that they are getting. So it increases the bandwidth. So using systolic arrays is much more better. Yeah, so if we look at the Python hardware simulation, we can see the like the structure will be a like we tried to use the clock model Verilog code, but um, to import the hardware architecture models, we have taken the Python code. Like there is no Verilog code for this project. The like to use the delays and everything, we use the NumPy array models to model the FIFO, FIFO buffers and local registers. And the real-time applications, as you can see, uh, in 5G telecommunications, for baseband, we use FFT for modulation, and for real-time signal processing also we use the FFT modulations. And in radar and sonar or radar and sonar usage, we for target detection we will use the FFTs. Like in medical imaging, like MRI and CT scans, also we use FFT reconstruction. Like from the like you can say it as like mm, using instead of DFT, we can use it for IDFT also. So you can say reconstruction. And for high resolution image, like reconstructing the image, you can use the FFT models. So this is the advantages in the Radix 4 architecture. The number of stages will be reduced compared to Radix 2. And since we are using the local memories and everything, the CPUs require more compared to us. So there will be no global memory access and latency will be reduced. And here, since it is Python simulation, we don't need any FPGA boards and everything. So let's go to the project. I mean, implementation of the project. Okay. So yeah, so this is our project. Let's run them all. Yeah, we are installing a number module to like for accelerators. It is imported from the number module. We can see here. This is the architecture. We will see this. Mm, yeah, these are the modules that we require for the display of the results. This is the here we have imported the architecture accelerator. So it's ready. So these are the computations for Radix 2. uh, like this is the systolic pipelining model of the Radix 2. This is further developed into Radix 4. Like we have used different models here, predefined naive models and our implementation systolic process so that we can compare both and we can show the results here. This is the Radix 4 process here. So it will count the computations like the number of operations the to see the difference. Here it will calculate the latency. So our Radix 2, oh, like since we have a complex number for everything, we have to compute separately for the real values computations and the imaginary numbers computations. Initially, we will fill them with zeros and then we will use the data, like based on the data we require, we will fill them. So as you see here, all the data is being stored in the local registers. Yeah. So here you can see the architecture of the PE structure. These are the equations for Radix 4. Uh, this is the systolic arrays representation. Like 16 n is equal to 4. This is 16 bits. So here it will be like this. Uh, so this is the systolic pipeline. Like each stage we will have a 4 Ps. Since we have all 16 Ps, it will be one stage input will be passed to others like that. Mm. This is the radix model. Like after delay, we will have multiply with the twiddle factors. With the twiddle factors, like this delay is for to get the data. To ensure that data is passed from this stage to the other stage. After this data will be getting here, and the twiddle factor multiplication and the additions and subtractions will be done here, and we will get the outputs. This data will be passed to the other stage. So, it is similar to the radix. I mean, as you know, radix 2, like in the first stage, we will multiply two multiplications in the stage 1. Like after that, it will be 4, like that. So it will be as you know, the data will be processed diagonally, like in the first element to the third element, the indexes. You can see that here. Just a minute. ఇది ఎక్కడికి వెళ్ళిపోయింది? Yeah, as you can see here, here when it is the when you're in the stage 1, when you are multiply taking only two elements, we can take the first element and the next element. After that, when you are taking to the second stage, where the elements will be from, we have four sets. One state will take the first element will take the third element and second element will take the fourth element. So similar to that, here we have updated the code, and in the next stage following, it will be we will have eight stages. So 4 to 4. First element will take the fifth element, second will similar to that. That's how, let's say we are using the size 16, it will take like this. For size 32, it will take first to 16th. Like as the stages are increasing, this will increase. So here we can see this is for 256. So 128 to 128 will be happening here. This is that. So that is the general naive process. This is the systolic array process. In this, we are using since 4 point. So we are giving all the four inputs at a time. So this will reduce the complexities. As you see, each stage have these many. So if you compare them here, the number will be very much less. This is for 256. So this is the twiddle factor equations and everything as I explained. So now let's compare the data. So here this is radix 2 for n equal to 1024. This is the number of seconds required for radix 2. So since let's say radix 2 is small, n equal to 1024 is small, so it requires the number this much. But when you compare this with the systolic array, this is the estimation for radix 2 systolic array, radix 4 systolic array. As we discussed, since there is there is very much less latency, this data is very much less. Here we can see the comparisons for every model. As you can see, this is number model imported. These are the naive model, basic models. This is the radix 2 stages. For each stage, this is the time. This is radix 4. And for comparison logic, this is the extra, like we have taken radix 2 latencies and radix 4 latencies. As you can see here, these are the, let's say, like if you are using 1024, the number of multiplications will be like, let's say we have n DFT. For that, the number of complex multiplications will be 4n square, and number of additions will be 2n square. Like it will be also around 4n square. So as you can check here, this is the increase of 4n square, complex additions and multiplications. The latency of radix 2, as you can see, radix 4 latency is very much less, and radix 2, since we have more calculations, it will have the it will require more storage. For radix 4, it will be very much less. Yeah, so this is our project. Thank you.